And so then we went down to this slide to, is it different from this picture in a hallway?
Right. We never saw this slide, so go ahead and start from here.
Okay, good. So the point is, you know, we have these pictures of railroad tracks, and we have this vanishing point where we have all these purple lines kind of converging off into the distance. And, you know, you change it to a hallway picture, and you have the same exact phenomenon going on where the floor is rising up to your midpoint of vision, the ceiling is descending, and you're asking yourself, why is this any different from this? So the question is, what do we know? So we know that things get smaller with distance. That's perspective. And so the current understanding for how that works, you could find this on, you know, physics of lens lectures online. But essentially you have two rays extending off of an image. An image is something that's contextual. It requires context. You don't receive an image from essentially one ray of light. It requires a crossover point in context. And so the top of the tree in this example, in the upper right is, and we're not going to get into the physics of lenses where you have an image closer than the focal point, you know, f2 prime there. Most everything is beyond two focal lengths away. So you have this tree here, and it gives off two rays and extends through your lens. They are reconverged as they cross through focal points f1 prime and f1 to create an image on the other side, somewhere between f1 and f2. And that image is projected onto the retina. So you see I have the eye there kind of represented. Mm-hmm. And so you can see how we move this tree out further and further away. That angle is going to get smaller and smaller and smaller as it has to converge across those focal points. And you can see how the tree is going to get smaller and smaller in that field. Where those two rays cross is that top of the tree between points f1 and f2 behind the lens, right between here. And so you can see how the tree is going to get smaller and smaller. So that's kind of the current understanding of how things kind of get smaller with distance, and it has to do with the physics of a biconvex lens. So far so good?
Excellent.
Okay. So that's the first point, is things get smaller with distance, and I think that's pretty apparent. No one's going to argue that too much. So the second part is small things do disappear. And so this gets into something called the angular resolution limit or the diffraction limit. And the main thing here is you just have to realize that as light travels through a physical barrier, in this case a circular aperture, it's going to scatter a bit. And it's going to scatter its rays on a background, let's say, in a certain pattern. And this pattern is called an Airy pattern. And it's a diffraction pattern. You see all these concentric circles. Those are just interference points, and they're creating bright fringes and dark fringes of where information is getting amplified and non-amplified, essentially. It's very similar to a diffraction pattern in water. And it just represents kind of something acting similar to a wave where the energy is focused kind of in the center, and it kind of ripples out with distance. So what you find is, or what Rayleigh and other people found in the late 1800s, you can pass this light through this circular aperture. The smaller the aperture, the wider, the larger this central disc. This is called the Airy disc. This central kind of bright fringe is called the Airy disc. The wider this disc is, and the larger this diffraction pattern. And the larger the aperture, the smaller the diffraction pattern. So think of it like you're trying to squirt something through a really tiny hole, and it's going to kind of spew all over the place and diffract all over the place. That's kind of how I view it. But when the hole is larger, you get a much more pinpoint light hitting the background. Does that make sense?
Absolutely. Okay.
So now what you have is and this is called a first order Bessel function. I'm not going to get into the math of that. It's actually pretty complicated. But all it means is that you have this central bright fringe, which is kind of up here at this point, and you can look at it a little better here with these ray diagrams down here. So you have like two diffraction patterns merging. So this bright fringe right here, this central disk, is kind of this central fringe right here. And there's two diffraction patterns merging in this case. So this person set up two circular apertures and two light sources, and they just started moving them together to see what point you lose this image and it becomes one. And so Rayleigh did that, and he found that this essentially this angle at which this happens is equal to the radius of this airy disk. And the radius of this airy disk is a 50% overlap point between two airy disks, right? Mm-hmm. And I'll show that here in a minute. And this 1.22 that he derives is essentially from this first order Bessel function. So that's all you really need to know about that. But the formula is that this angle between these two merging patterns is such that it's 1.22 times the wavelength of light divided by the diameter of the aperture. So the larger the diameter of the aperture, which was back here, right? The smaller this radius is going to be, and the smaller the angle is going to be, and the better the resolution of the observer. So what I mean by that is if you have two merging patterns here, and you start to merge them, if you can define how small this disk is in the middle for a longer period, you will resolve more for a longer period. But the wider this disk is, okay, as these two merge, they're going to get indistinct a lot sooner. So the higher the angle, your angular resolution, the lower the resolution. So in other words, the larger the angle, the poorer the resolution. That's what I'm trying to say. Does that make sense?
Yep.
Okay, and so I want you to think of this as the distance when the two objects are no longer distinguished from one another. And you can kind of see that here. They're 2, and then right here at 50% overlap, it essentially becomes one image.
Right.
So as an example, two close stars become one, or the hair merges with the floor, or the plane becomes the sky, or the bug becomes the wall. Essentially, information is lost.
Right.
So I have kind of some patterns here to look at. So you can picture these as two diffraction patterns that are going to start to merge. The brown line is the distance between these two central airy disks. So right now they're pretty far away from one another. And these black lines here are just the interference points, constructive interference zones within these two patterns. And you'll see as we have a lot of them right now, but they're going to get less and less. But I just want you to kind of focus on your vision and how you view these two distinct objects as we merge these two together. So I'm going to kind of go through the screen now. So here's the first distance, and here's the second one, and the third one, fourth one. So I'm just moving it together. Okay, so you see how that, I'm going to go through it one more time. You see how there's two distinct patterns right here, right? Mm-hmm. And I'm going to merge and merge and merge and merge and merge. At what point do I say, that's pretty much one pattern? Well, what was found was that it's at this distance right here. So this distance right here is the overlap point of the two central airy disks, where you no longer think of this as two distinct images. So if you want to concentrate on the upper left corner instead of just in the central, I'll show it one more time. So right now we have two airy patterns, so we're going to merge them. Okay, so that's essentially Rayleigh's criteria. Okay. Gotcha. Mm-hmm. So how I envision this is you have these two rays extending through your convex lens, and they are providing contextual information to the observer. And at a certain point, the two rays are so far or so close to one another that there is no context that is created for the observer, and they just do not distinguish that object from another. And so I have them as kind of these two rays, right, are having their own diffraction patterns. And the aperture in this case for the eye, right, is just your pupil. So here's your convex lens behind your pupil. Your pupil's like right here. And as the rays go through, they diffract. They get into these, they have this diffraction pattern within them. And as these rays get closer to closer, because the tree in this case is further and further away, well, you're going to start to resolve less and less of that portion of the tree. And it's going to start to merge with its surroundings. So right. As this thing merges down, at a certain point, it becomes unresolved.
So one way to look at this might be that if you're outside and you're observing a fly that's really close by, you're saying there's a ray of light coming from both the top and the bottom of the fly, and after going through our pupil, it's at a size and a separation enough that we can see that image. But if the fly flies, 20, 30, 50 feet away from me, because those rays coming from the top and the bottom of the fly are now coming so close together that ultimately no image can be resolved, and that's why I don't see flies 50 feet or 100 feet from me, correct?
Right, that it's getting smaller with distance, and at a certain distance, it's just going to merge with its surroundings. You're not going to resolve it as a distinct image anymore.
Okay, great.
So how small can this angle get where we talked about things getting smaller with distance? Well, it gets to be the Rayleigh criteria. And once it reaches that point, it's kind of merged with its surroundings. So I do a practical example here. I'm not going to go through it, but you bring up a perfect point, actually. So we'll see if we can see a small bug 20 feet away on a wall, okay? So you use the Rayleigh criteria up here, and you can determine what your resolution limit is approximately for the human eye in this case. So you'll see that the Rayleigh criteria is not quite perfectly accurate to what we actually see with, because you notice this angle, 0.00874, that's really good resolution, right? So we actually see at 0.002, or 0.02, excuse me, that's right. One arc. So this is actually like twice as good as we actually see. But for most purposes, the Rayleigh criteria is actually pretty good. But when you use this, you get this resolution limit. We'll say we have this resolution limit for this example. Okay. And now you can use it to see, because this is such a small angle, you can use it just with regular trigonometry. And you can assume that it's basically the small angle formula. You can use a right angle. Because this is like 80, this is 90 degrees, but this is like 89.9. It's close enough, so you can use this approximation. Right. And so a simple formula is going to be tangent theta is equal to the opposite over the adjacent, right? And so in this case, it's the height of the object divided by the distance. And you can rearrange the formula to say that the height of the object should be equal to the distance observed times the tangent of theta, in this case 0.00874. So I plug these numbers in for our bug being 20 feet away, so that's 6.1 meters, and you come to approximately 1 millimeter. So if our bug is greater than 1 millimeter, we can see it. It's not a wall, essentially, but if our bug is less than 1 millimeter, we can't see it, and it's essentially the wall. Mm-hmm. And that's why I'm kind of saying down here, note, human vision is typically 1 arc minute or 0.02 degrees. So Rayleigh criteria overestimates resolution in practical terms, i.e. the bug versus wall threshold is closer to maybe 2 millimeters at 20 feet. Okay. That's a practical example. So that's the basics of how this is going to be used, okay, throughout when we're kind of estimating size and what we can see and what we can't see, okay? So what is a vanishing point? So when I'm going to take these kind of stuff that we've talked about, and you're going to kind of combine them. So to me, it's the smallest, most distant visible angle at eye level from information convergence through a convex lens. So I think of this point as the smallest perceivable point that is radiating light outward towards you, or let's say it's the point where your convex lens is converging all information to that single point, and it has an angle. It's the smallest observable item, the furthest away. So it's the smallest resolvable point, or point where objects vanish. We see in terms of angular size relationships, therefore this point has a defined angle, which we talked about, and it is not infinitely small. So I often ask people, well, do we see forever? And the answer is no, we don't see forever, obviously. We define the smallest resolvable angle as the angular resolution limit, and the angular resolution limit is commonly given by the Rayleigh criteria. So since angular size is dependent on distance, the vanishing point has a defined distance. And so what I'm saying here is this thing here is not going to change because I went indoors. It's the same phenomenon because I'm inside as it is outdoors. And so how I've defined the horizon distance is essentially that the observer height is proportional to their distance. The higher they get, the less compression of the visual field, and the further they can see. And so if I increase my height, I see further because I'm compressing less of the floor. And I'm going to get into that here in a minute for how the tangible surface compresses what you see. But that's how your distance is calculated, is essentially proportional. So if I'm 12 feet, I see twice as far as when I'm 6 feet using this same angle. Okay, so it's just two similar triangles using this angle. Consequently, within perspective, however, now you're taking yourself away from being the observer and you're looking within what the observer sees. as an object moves away from you, it's going to get smaller, and that's going to be inversely proportional to the distance. In other words, something gets twice as far away, it's going to get twice as small. Okay, so height is inversely proportional to distance. You can take any two objects' heights and any two distances, and they should be proportional to one another. So I think in my first video I did an example with a door. The door is a certain amount of angular size at a certain feet away, and if I double the distance away from that door, it's going to get half the size. Double the distance, half the size.
Right. So, okay. It's like the laws of halves and doubles as far as perspective goes. Okay.
Yeah, exactly. So how does perspective alter the visual field, right? So, and subsequently this point. So the visual field is split due to the nature by which light is focused on a biconvex lens. So what is above the center of the convex lens is going to get focused as an inversion on the back of the lens, and what is above or what is below the center of the lens is going to get focused, above the lens, right? So if I go back to where was it? Like this, for example, right? So when we see an image, it's always inverted on our retina, and camera sensors and our visual cortex and everything, they take this image and they upright it again so that we don't see things upside down. But that's how this image is actually imprinted on the surface of the sensor, okay? So anything above this purple line, right, is going to be rendered below the purple line. Anything below the purple line is going to be rendered above the purple line. Does that make sense? Mm-hmm. Okay. So again, whatever is above the center of the lens occupies the upper 50% of the image, and whatever is below the center of the lens occupies the lower 50% of an image. In other words, the vanishing point rises to your eye level, okay? So the vanishing point is essentially this non-refracted central point within the lens. The closer one is to the floor, for example, the more limited the angles with which one views the floor, yet it will still occupy 50% of the lower visual field. So does that make sense? Because I don't want to move on.
No, it's really interesting and it actually makes a lot of sense. I guess where you might want to explain to people again is how you said that the image reverses, but which part of it falls below and above the central line there. So you might want to explain that again.
Well, all it means is that the camera, or the brain in this case, has to take this image and upright it again. Mm-hmm. So that's done on the business end over here, right? We don't worry about that. But the optics of just the physics of a lens is such that we call this a real image, but this real image is an inverted image when it gets through this lens and is created on the other side. And that's just has to do with because these lenses, these focal points have to get, this is one point of information going through this focal point, and this is the other aspect of information going through the second focal point. When those two get crossed over is where this thing is rendered on the sensor. Gotcha. And it just so happens that the camera system or the brain has to take that information and flip it up the other way, but that doesn't mean that information can cross over from one field to another, okay? So does that make sense a little bit?
Yep.
It's important because what it means is that whatever is coming in below this purple line, essentially just think of it as it's always below the purple line. And whatever's above the purple line is always above the purple line, and this purple line represents your eye line. Essentially similar, it's going to intersect at a vanishing point somewhere out here. Mm-hmm. And so as your eye, as this thing moves up and down, right, this purple line moves up and down with it. Mm-hmm. Okay? That's the main point of that.
Okay, good. I think we got it. Okay.
So what it means is if you were to converge, take all these light rays that were being reflected from the sun or something like that off a building, and they are getting, they're radiating off an inverse square law, let's say, and then your lens is taking all that information and reconverging it back down again, you end up with something like this, which is kind of a one-point perspective view. Mm-hmm. And I put a little building there in the middle so you can kind of see where the building is. All right, so now what if I take my observer and I push them lower to the floor? Okay, well now I'm still going to render whatever is above the lens above the 50% mark, and whatever is below the lens as below the 50% mark. So if I take my perspective view right here with this purple line and I lower myself now down to the floor, Well, when I look at this image, I'm still going to see 50% of the floor as the lower aspect of vision. So if it's not clear right now,
No,
I'll
it's
show
clear.
it here in a minute, and people will understand what I'm talking about. So I just want to do some quick definitions. So this is people kind of call this Muppet vision, right? This orthographic view, when everything is kind of rendered, when they want to say what is being lost in the distance, they kind of represent it this way.
Right.
But if you were to take this and you were to say, like, you had paint on the walls, that's what this is, just like paint on the walls.
Okay.
But these are like 10-foot intervals, right? And then you have these kind of parallel lines going with this purple line, and representing kind of the floor and the ceiling, but they're just moving off into the distance. Well, these lines right here that are moving parallel to this purple line are called orthogonal lines. And these lines that are moving transverse are called transversal lines. And when you render this down into perspective, you'll see how these start to look. So transversal lines are going to be these lines right here, and orthogonal lines are going to be these radial lines extending inward towards the vanishing point. And what you have to remember is that 10 feet right here this is exactly the same as 10 foot here, and this is exactly the same as 10 foot here. But when you render this in perspective, 10 feet is going to be larger here than it is over here. And I know that seems like a dumb point, but it gets more complicated. So Just remember that 10 feet is represented in perspective a lot differently than it is in orthographic terms, okay?
Gotcha.
Okay. So here's kind of an example of what I'm talking about with this 50% phenomenon. So if you were to take just kind of a diagram of perspective, of 1-point perspective, and you were to compress things downward, you would kind of get a representation that looks like this, where this image by itself, these are like buildings, let's say, moving off into the distance, or any object for that matter. And they're going to maintain their relative angular size because they didn't move anywhere from the observer. You just changed your height.
Right.
But as you get lower to the ground, you're going to be pressing more of the ground into that lower 50% of vision, right? Everything that is getting converged below that midpoint of that convex lens is getting pressed lower and lower to the floor, okay?
Brilliant.
So you're seeing much less of the floor, actually, because you're pressing yourself closer to it. So the closer you are to the tangible surface, you actually start moving the most distant angle at which you can see closer to the observer. Okay?
Right.
All right.
So, basically, if in this little hallway example you have up top here, if we had a penny lying on the ground in the first image on the left, we might be able to see it. But as we start to lower down, that penny's going to disappear just because we're trying to fit more of the ground into that 50%.
Exactly. We have to compress, in terms of that lens, we're pressing more information into that lower half. And it's just getting lost a lot sooner. We're inducing that angular resolution limit at a closer distance. That's the bottom line here. So the disappearance or the distance to the vanishing point is dependent on the observer height, and because the proximity to a tangible surface. So as I press myself lower to the floor, I'm limiting the number of angles at which I can view distant objects. But at the same time, I'm expanding my view of the ceiling, right? So if I'm in a subway and I press myself near to the wall, let's say, and there's a bunch of pictures on the wall, I'm going to see less and less of those pictures as I move myself closer to the wall. But I'm also going to see a lot more of the opposing wall's pictures. Okay, does that make sense? Because I have a better angle to them. And the same thing happens to the ground. As I get closer to the ground, I see more of the ceiling. So let me see if I had anything else here. So as the angles diminish, the information is compressed, the vanishing point is brought nearer to the observer. And so we're going to kind of see that here in a minute. So what I did was I took some golf balls and I took a hallway and these lights, and I put these golf balls right below the light, directly below the light, and I measured the distance between the wall and the lights, and I did about 130 feet worth of golf balls, the first one starting at about 20 feet away from me. And then I raised and lowered my iPhone from about 8 foot down to about 0 feet, and it's 1 centimeter off the ground at this height right here. And so I just wanted to see how these golf balls, you can see them here. I kind of blew the picture up so you can see the golf balls right there and right there and right there and right there. They're in a straight line, and they're moving off to this light that I put just 130 feet away, okay? And that's where the last golf ball is. And so as I compress my height, you see that obviously they're getting more and more shallow within the frame, okay?
Yep.
So, but my point here is just that you're seeing less and less of the floor, and you're seeing a lot more of the ceiling as I compress myself lower to the floor. And that's all I wanted to say for this part right here.
Okay, perfect.
So hopefully that's clear to everybody.
Should be very clear. The only thing, they might not be able to see the golf balls, but again, I'm sure it's just because we're looking, this is like third person now. By the time you're showing it, it's going on my screen. I'm showing it on the live stream, so people might not be able to see it. But just point out with your mouse real quick where those golf balls are.
Yeah, here's one right here. If you can see that. That's the first one. There's a second one right here.
There you go, yeah.
And a third one, fourth one. And I start to lose it here too on my screen.
Okay.
But I blow it up and you'll see here in a minute.
Perfect.
All right, so what I did was I blew all these images up and I put markers, color-coded markers on where the ball was in relation to which light. Okay? So the red line here, right here under this light is also this red ball.
Okay.
Or this red line to this ball. The green line right here is the ball that was placed under this light that has the green line. And I did that all the way down the hall, okay, to 130 feet. And so essentially you could think of it as it's like a tall 8-foot object, right? That's just 10 feet spaced apart and moving away from you. Mm-hmm. But I did it just with lights and golf balls. So
gotcha.
All right. So when I do that, and then I take away the image, and I just see kind of how these things space themselves. You see that as I got closer down to the floor, I was seeing many more tiles, mm-hmm. right, before even that first golf ball. And you can see how crunched together all these lines are for those golf balls.
Right.
So as I press myself lower to the floor, these angles are getting smaller and smaller and smaller. As something is moving away from me with distance. So if I kind of take these lines and I kind of pull them out to the right a little bit, and then draw a vertical across them, you can see kind of how they're scaling. So this is kind of like I'm trying to show you how this may represent itself a little bit from a side view. Mm-hmm. Okay, even though this is not, what you're seeing,
right.
But you can see kind of how this creates a curvature for you, right?
Absolutely.
How objects could be perceived to be, because it's an exponential decrease, how it's essentially a parabola, right?
Absolutely.
Okay. And so I tried to kind of pull that out and say, okay, now this is the side view, right? So as I am towards the ceiling here, right? So that's 1 foot to the ceiling. I'm 7 feet to the floor, and I'm crunching all that information, along the ceiling. Mm-hmm. And as I get lower and lower down towards the floor, I'm pressing more and more of the floor against that lower half of vision. Okay. So again, it's just the distance to the tangible surface is dictating how information is compressing within a visual field. Okay.
Wow, man, this tells me so much even when we start talking about going higher and higher and why we lose sight of stars. It's just crazy. Great information. Keep going.
Yeah, sure. So don't worry about the wording up here too much. My main point with this, and I know it's busy, if people want to get kind of the details on this, just please watch the video. You may have to do it a couple times, I realize, but I'm just going to try to break this down. So, Jaron, you mentioned the law of kind of having, right, mm-hmm. within perspective. And I didn't really realize that before until I kind of started playing with this hallway example. And so what you see is that if I'm at a 1 foot observer, I can actually see the tile markings here. And I saw the tile markings on all these images. I had to blow them up a little bit, but I could see how many tiles were within each picture. And so here I'm about 1.5 feet. Now the law of halves says I take whatever my purple line here is, and I divide this lower half of the image in two mm-hmm. by 50%. And whatever I see in this lower part of the image here, let's say everything below the 1x, below the red line, is my kind of starting point. And I just keep doubling the amount of information. Whatever's contained in here, I keep doubling it with every half, every subsequent half. So if I take the purple line now to the red line and I half it, that's the orange line.
Right.
If I take the purple line to the orange line and half it, that's the yellow line. And I keep doing this. And that gives me a double compression each time I do that. So I'm seeing 1.5 feet right here. Then I'm seeing 3 feet. That's pressed into this small area. Then I'm pressing 6 feet into this area. Then I'm pressing 12 feet into this area, and so on and so forth. You're pressing more and more information within these lines as you move away. Okay? So, and it works out. The math actually works out. So this is the 7 foot to the ceiling, 1 foot to the floor image, and I put it next to the 7 foot to the floor, 1 foot to the ceiling image. Okay, just as like a proof, you know, or a
right.
Just to make sure that what I was seeing was the correct amount. And so you can use the number of tiles along the ceiling, and you can use the number of tiles along the floor, and you come to these numbers. And so at a 7 foot height, I'm seeing roughly 11 tiles. Then it goes to 22, and you can see because the green line and so let's say the green line and that's 10 feet, I know, right? Mm-hmm. Because that's a 10-foot marking. So the green line to the yellow line is 10 feet. And I know then that this distance to this distance, I could see how that's roughly 22 feet, right? Mm-hmm. And this is roughly 44 feet. You can see the number of lines that are contained within that space.
Right.
And then 88 feet, and it goes on from there, okay? So that's all I'm saying with these kind of complicated pictures. But when you start summing these things, right, and you say, okay, well, how many lines do I get before I get to some crazy number?
Right.
And so we know that, again, if I'm using the smallest angle resolvable as theta, right? So I would say that if my height is 1 foot, then that's my observer height, that's O, and I'm dividing it by the tangent of theta, which is 0.02 degrees, and I'll come out with a certain distance. That distance is 2,865 feet. So I'm estimating that I should be able to resolve at least 2,865 feet, which is about a half mile away at a 1 foot observer height.
Right.
Okay. And so I started compressing these numbers down, and I just started with 1.5 feet right here, and then I went to 3 feet and 6 feet, and same thing with 11 feet, and to 22 to 44 to 88, and I just started summing that up. Right. As I went further and further away, I'm just summing all these numbers to get a total distance. Mm-hmm. Okay. And so what you find is that if the purple line is about 819x for it to match up with this resolution angle. Okay. So it doesn't come out to be a clean number where I wish it was like, oh, it turns out it's 1024x, and that matches perfectly with 1 arc minute of resolution. Right. Well, it's like 819x, but it actually works out for this particular phone under this particular circumstances for all these heights. And so it comes out, you'll see that the difference between the two is actually 100 feet right here. So as I extrapolate this 1.5 feet that you see right here all the way to the purple line, well, it comes out to 2,640 or 2,764 feet at 819x. And so that's very close to what the resolution limit would be. And so you might say, well, wouldn't that line continue on into infinity or whatever, right? Because it was a parabola. But again, we know we don't see forever, so it can't do that. And I'll kind of show how small those lines actually get here in a minute. So this is just another example. This is now the 3 foot to the top and 5 foot to the bottom versus the 5 foot to the top and 3 foot to the bottom, and how many tiles are different between those two. And now it's about 8 foot here and about 5 foot here, and then you double, so on and so forth. And I just inverted those two. That's why the white is white over here and white over here. The black is over here and black, because they're they're the same as one another. And so what you come to is that at 819x, the number is 1.55 miles for the 3 foot height versus 1.63 calculated for theta. And for the 5 foot height, it's 2.78 miles versus the calculated 2.71 miles. So they're pretty close. Same thing again here. Now I'm going down to 1 centimeter height. I'm really close to the floor. And so in this one, I put in the put in the lines themselves. So you could see what, between this blue line right here and this purple line, how many compression points I did to get to 819x.
Right.
So it's very small, okay? It's like down to a pixel, right? So I can see how this would work. But so between, if I split the blue line and the purple line to 32x, that's this line right here, I'm going to split that in half to 64. I split that in half to 128. I split it again to 256. I split it again to 512. And then I don't quite get to split it one more time into 819x because I just kind of lose resolution at that point. It just becomes like a merged line.
Right.
And so the other caveat I want, so if I calculate these two out here, if I just, and so what I calculated is that you're seeing about 2/3 of an inch now within the red line down to the bottom of your image is only about 0.6 of an inch, which is kind of crazy. But think about that in terms of how much you're taking up within this image.
Right.
That's 1/4 of the total image is just 0.6 of an inch.
Right.
When you're 1 centimeter off the ground.
Crazy.
And so that keeps doubling and doubling and doubling, even all the way up to this green line. You're still only seeing 5 inches worth of floor. And so the way I don't know if it's in this video actually, but if you go to the video, I do a ruler test where I stick a ruler right in front of this thing and I tape a 1-inch mark on it so that you can see that indeed this is only 0.6 of an inch. Because essentially it goes to right here, and then I have to calculate the vertical field of view loss. But it works out pretty well. So, as long as everyone's clear on that concept, that you're just doubling the distance, having the size, and that essentially to a certain point, things will not compress anymore. You're just going to lose them as essentially a line, and that's really what I want to impart here. And so if you can see that, you can't quite see the golf balls here. I'm pointing to the first golf ball right now. Okay. So that's that first 20-foot golf ball. Look at how close it is to the purple line already.
Jeez, yeah.
Okay?
Right up against it.
So how long can that go like that before we start losing information for these balls, right? So I blew up the image, and you can see if I were to extend this purple line right here out this way, it almost crosses just above this first golf ball. And as perspective, so essentially you're seeing like this plateau effect within perspective. It's almost like, let me see if I can go back to here. So you see how this line, so this is 1 centimeter off the floor too, I believe, or this might be, this is 1 foot off the floor. So this is 1 foot off the floor. You see how shallow this is getting?
Right.
Right. And you see how steep it is here. You're seeing a ton of golf balls, when you're 7 feet off the floor, but you're seeing them basically in a very shallow plateau region within perspective at the closer you get to the floor. So so each one of these yellow lines is how many feet away I am. And so I marked the 90 to 100 foot mark. And that to me represents the true horizon for this particular image. Okay. So this is the true horizontal vanishing line for this particular image, is at the 90 to 100 foot mark. That represents this purple area right here. Okay. And that's these golf balls. After this point, in my opinion, everything is going to start to set. Okay?
Wow. And
I'll kind of get to that in a minute. The other point I wanted to make within this is that, because I'm 1 centimeter off the ground, do I see, this is about a 450 foot hallway. Am I seeing a centimeter off the ground 450 feet away?
No way.
So no, I'm seeing a centimeter off the ground 95 to 100 feet away. Okay? After that, the upper visual field is starting to set within the lower, and so I'll go over that here in a minute, because it creates a horizon gap. Essentially, there is a gap of vision now between the upper and lower field where information can set within it. That's the theory I have anyway. So let me play this one real quick. Did this mess up your imaging? It kind of did, probably, huh?
Let me see. I'll shrink it down a little bit. You're fine. Go ahead.
Okay. So what I'm showing here is that this was my 1 centimeter height right here, and you can see how the horizontal line here represents now the corners of the walls, and so, but all the orthogonal lines still maintain their relationships, but what is pressed along those lines is different. So what I want to show here is that just because I'm 1 centimeter off the ground, perspective doesn't change if I go outdoors. So I showed in my first video how if you were to take a perspective view and you were to rotate the wall, or the left and right wall away from you, like let's say they're pivoting off this central vanishing point and moving further and further away from you off into the distance.
Gotcha.
What would you eventually be left with? You would eventually be left with something like this.
Right.
In other words, if you had no tangible walls to view any object along, you would see somewhat of this image.
Right.
Now, the minute you put something within that visual field, like a bush or a ball or something like that, it's going to line up along these potential lines, okay, towards a central vanishing point, wherever that point is for your convex lens. But without that reference frame, you have essentially this kind of a view.
Mm-hmm.
So if I have now my 1 centimeter height, and let's say I blew away the walls and the ceiling of this particular building, and I'm still at 1 centimeter down on the ground,
right,
and I'm just left with this massive expanse of concrete extending off for miles. And if I just, so that it's kind of look like something like that,
gotcha,
right?
Yep.
And now let's say instead of this concrete floor, it's just a row of crops. So I'm really close to the crops, okay? Like they're extending, these crops are like extending off into the distance instead of a concrete floor.
Gotcha.
And now I just decide to stand up, okay? This is essentially what you would see. It's just perspective. You're just altering your landscape, but perspective remains the same.
Right.
And that's what I wanted to impart. So in other words, is this the leading edge of a sphere, right?
Right.
No.
No.
It's like a hallway, right? But you've removed the walls and the ceiling. Okay?
Perfect. Yep.
This is a data table. So I was hoping there's a guy, BuzzDev. I don't know if you've seen some of his work. He does really good Blender work.
Oh, yeah.
So we've been talking a little bit about trying to figure out how to really map perspective within a 3D program, because it's not accurate how it's rendered for how we actually see the world, like in these exponential terms. So we're kind of working together. That's kind of my next thing. I think we talked about that, is what is the perspective formula, and that's a lot more complicated. So I'm trying to work that out, but it might take a little bit of time. And like I think we talked about as well, if we can kind of load the boat with folks that can kind of take some of these concepts and move with them, and add their level of expertise to them, then I think we grow as a community. So
absolutely, yeah, that's the whole point of these presentations and the videos I do. My hope is that people see things I missed, or same thing with you. You've done a great job here, but people might see something and it makes them think of something, and they go develop a video or an explanation that helps the community in whole. So totally agree.
Yeah. So if I go kind of back to what we'll call Muppet vision, this orthographic view, I now know that I don't see as far along the floor or the ceiling, depending on my distance to the floor or the ceiling. So when I put this in a side view relationship, I know that when I'm 8 foot up, I'm not seeing very far along the ceiling. Okay, so this orange line is shorter now, but I'm seeing much further along the floor. Okay, so this red line's a little bit longer. And when I'm at a 4 foot height, I'm dead center in the middle of this 8 foot hallway. Okay, so I'm seeing equally along the floor as I am along the ceiling. Okay, and now I'm at a 0 foot height or a 1 centimeter foot height. I'm seeing much of the ceiling. I'm not seeing a lot of the floor. So when I rotate these things down within perspective, and you kind of start to see how you would render a 1 point perspective view, you see kind of how the balls would move away from you with distance. So that's just kind of what my point here is that there's somewhat of a gap, in my opinion, that occurs within your vision as you collapse these two down with a convex lens. Does that kind of make sense, just roughly conceptually?
Yeah, absolutely.
So here's what might get a little complicated.
Well, go back one slide. I maybe have a question. Are you saying that would occur no matter the eye height? There's always going to be that horizon gap, or is it only when you're blocked by something low? So the image on the right that shows all the balls lined up and you're below the balls, would it also happen when you're above them?
Yeah. So it just, the only thing that determines how much of something you're seeing is how close you are to that surface.
Right.
And so if I'm close to a ceiling, I don't see very far along the ceiling, but I see along a lot of these. I see all the golf balls really easily,
Gotcha.
right?
Yep.
As I get, lower down, in this particular case, the golf balls are at a diagonal, okay? But if, let's say, they were straight down your eye line, you would see something like this, right? You would see that first ball is going to be really big because you're closer to it, okay? But it's going to diminish in angular size pretty rapidly as it moves away from you. And it's going to move away from you more in a straight line, because think about that first ball, that 20-foot ball is already at the purple line almost within this view. Whereas if I'm high up and I'm viewing these balls along the floor from a higher view, their angular size relationship actually doesn't change very much as they move away from you, because you're further away from them. But I wish I had another view to kind of show that. But if you can kind of picture lines radiating out towards from the observer out towards these balls, they're relatively constant when you have this kind of relationship. But if you were to do those same lines along the orange one here,
right,
they're much more shallow, and they get more compressed a lot more easily.
Gotcha.
So that's why this angular size relationship is a little bit different between this view and this view. So, and I go over that. I think it's part 3, I think, where I go over that. If people want to check that part out. But all it means is that the further away something is, the less it actually changes in angular size. The closer you are to something, it's going to rapidly diminish in angular size as it moves away from you. But so, like, if you were watching a car from the 5th floor of a hotel, and you watch it travel away, it's going to diminish in angular size at a certain rate. Now, if you get down to where the car is on the pavement, the car is going to be much bigger because you're closer to it. But as it moves away, it actually is going to get closer or smaller a lot faster than it did when you were on the 5th floor. Okay. All right. So the main thing here is that I just want to impart here that things still disappear at 2 theta. Okay. So because information is radiating off to the observer at an angle bisected by your eye line, right? The smallest amount of information is going to have a theta above the eye line and a theta below the eye line. Okay, so if I'm at equal compression within a hallway, whereas the observer is directly in the middle of the hallway, the height to the ceiling is 4 feet, let's say, and the height to the floor is 4 feet. Well, the object is going to disappear as a single point, okay? Because all things are going to compress at an equal rate.
Gotcha.
Okay. Now, though, if I press myself lower to the floor, okay, I've changed the ascent rate at which that object is going to hit the purple line. Mm-hmm. It's going to hit the purple line a lot sooner than it did before. And so what ends up happening is, once it hits the purple line on that compressed lower field, as it moves away, it's actually going to start setting with distance, okay? And so I've kind of depicted that here. If you have this clock tower and it's X amount of feet and it moves away, if you are equally compressed between the floor and the ceiling, it's going to disappear as a single point at a certain distance.
Gotcha.
But if I get closer to the ceiling, this clock tower is going to reach this purple line along its top portion a lot sooner than along its bottom portion. And as it moves away, it's going to kind of have this setting phenomenon. But it's still going to disappear in total at 2 theta. So this part here, this is going to be theta, and whatever my height is from the ceiling to the observer, that takes up this part of the clock tower. That's what you can assume could be potentially lost. But I don't want to say lost because it just means that it's reached the purple line. This amount of distance has reached the purple line at theta across this compressed visual field. So that whatever is remaining of this clock tower at this distance right here now disappears at this theta rate, whatever your distance is from this point to the floor. And the opposite occurs when I have a compressed lower visual field to the floor.
Right.
So I know that's complicated, but what I want people to realize is that this clock tower may not actually reduce in angular size differentially much at all, but the rate at which it ascends to the purple line is different depending on your distance to the tangible surface.
Absolutely.
It reaches the horizon line quicker when you are closer to the floor. And so if you're kind of thinking ahead, the point is that you are always closer to the ground than you are to the sky, right? So things are always going to compress differentially against the ground than they do to the sky.
Beautiful. Yep. Makes all sense.
And so this is the basic argument. So if everyone's still with me, this is kind of the argument. We see the world by angular size. The smallest observable angle becomes the vanishing point and or line if you don't have any walls.
Right.
Things get smaller with distance. We talked about that with the lens diagram. Small things disappear. We talked about that with diffraction limits. And then you combine these two to say small things disappear with distance. Okay? Secondary to a couple of different things. The compression rate, right? Your distance to the tangible surface and where you've put that vanishing point. And then this kind of horizon gap, this setting objects phenomenon.
Right.
The second part is then going to be how small obstructions can obscure things from the bottom and how they can make things disappear with distance. And that's because that ascent rate for perspective ramps up really quickly, and you have this long plateau period, right, where something, if it were to raise above your eye line just a little bit in the near ground, would obstruct something, that was diminishing in angular size.
Absolutely.
Far away. And so we see that with waves, and I'll show that kind of as an example here in a minute. And then the final thing we can talk about briefly is just the upward refraction of light, and how that may come into play. The best way to think about this is refraction is occurring prior to information hitting the lens or the aperture, and diffraction is occurring afterward. And we'll get with that here in a minute. How am I doing on time, by the way?
I'm not worried about time. I think this is really good information that people need to see and recognize. What you're describing here is exactly what people are seeing when they go out and they observe, say, buildings that are partially covered, the bottoms of them by water over long distances, or maybe they see, what looks like the horizon line at just 3 miles away. And then if you're able to see 50, 60 miles, well, of course, at that distance, things have fallen past that setting point where all of a sudden you're going to get some objects that are setting to your perspective, but it's because you're so close to the ground versus to the sky. So I think it's it's really perfect what you're saying, and I'm not constricting on time at all, so just continue.
Right. They're essentially ascending to that purple line at a fast rate. And once they hit that purple line, what happens next, right? Well, they start to set as they get further away.
Right, and if you're talking about waves that are 7 to 10 feet high in front of you, you may not really notice that. You're at the ground, you're only 6 foot tall, looking with your camera across a huge ocean surface. But if you're seeing things that are 10 feet high only at 3 miles, of course they're going to block anything of any size that's behind there. Well, not completely. Obviously, it depends on what size you're looking at. But if you're looking at like a clock tower like you were looking at, you're much closer to the bottom of that. Therefore, that angular resolution, below your eye level is going to ramp up quicker.
Yeah, and something that's nearby that's relatively small could obstruct that clock tower as it moves further and further away from you because its size is getting smaller too. So, so essentially, what the argument boils down to, and why I have this graphic in the front of all my videos, which is down here at the bottom, is essentially that from a 6 foot observer height, we see roughly 3 miles, and to me that's because this theta angle here is dictating that. And then coincidentally, and also 6 feet worth of information is lost to the observer. In other words, it moves into this vanishing point and disappears at 3 miles, right? So this observer worth of information is going to ascend within perspective and lose itself at this distance. So for instance, if you were to have a 12-foot object and it were to move away from you, or let's say you had two 6 feet objects and they were to move away from you at distance, well, at 3 miles, you're going to lose one of those, and you're only going to be resolving 6 feet worth of information. So what? When you have these two kind of phenomenon going on where things are disappearing with distance and you can only see a certain distance, right? Well, so what? Okay. So that gets us to kind of this curvature issue.
Okay.
So they took this phenomenon across this resolution limit of 0.02 degrees, and they created R. And this is my opinion of how they did it. There could be other ways that they did it, but this is how I envision it. They observed that height was proportional to distance observed, such that a 6-foot observer could see 3 miles. To obtain the drop, they observed or extrapolated that 6 feet is also lost over 3 miles. So with a 6-foot drop at 3 miles and a 6-foot observer being able to see 3 miles, again, where theta is now not just 0.02 degrees, but something much more specific, 0.0217 degrees, we derive a tilt angle across 2 theta at 0.0434 degrees and a drop from eye level of 12 feet. And you can now derive R. So essentially they took these two triangles and they, stacked them on top of one another, and allowed for this curvature.
Right.
Because they kind of assume, and I don't know how it came to be this way. I assume they just saw that boats disappeared bottom first, or something disappeared from the bottom, and maybe they started to think, well, this must be only from a curvature phenomenon. And so that's how they took these two issues and applied them to one another. But again, you're just seeing a single object disappear at 2 theta, right? That's all that's all the tilt angle is 2 theta. So if you look up Walter Bislin's, he's got the latest, greatest Earth curve calculator. You see that when you plug in observer height of 6 feet, object height of 6 feet, and a horizon distance of 3 miles, you're going to come to a tilt angle of 0.0434 degrees, dip angle 0.0434 degrees, curvature drop of 6 feet, and a drop from eye level of 12 feet. And I've kind of diagrammed that here. Okay?
Wow. Yep.
And so this is kind of as an aside. Recall that the disappearance rate for a given object toward the vanishing point is 2 theta, right? Information above the center of the lens, information below the center of the lens. And as an aside, also keep in mind that objects smaller than theta, no matter where they are lost. So just because I have a vanishing point at 2 theta off here in the distance doesn't mean that things can't be smaller and lost to the observer here, right? I can be looking down a hallway with a distant vanishing point, but still lose a bug that's 20 feet away from me. So the reason I say that is because some people have kind of brought that up in my comments, and I've had to kind of go back and forth on that. So I just want to impart that.
Right,
so
absolutely.
If I have a 6-foot guy here who has 6 foot worth of balloons and I'm in a 12-foot corridor, when is that going to disappear? Well, it's going to disappear at 2 theta, okay? 6 feet above the eye line, 6 feet below. So they're going to disappear at 3 miles, and they're going to disappear as a single point. Okay?
Gotcha.
So now I take this phenomenon, right, which we already described this way, and essentially this is your eye. And if I just rotate 2 theta, this is also 2 theta, and you rotate it down, you come to see how they possibly derived the tilt angle. And so we can do that here again. So we can take our arc angle of 2 theta across an arc length of 3 miles, or we can take the height drop of 2 theta as 12 feet across 3 miles. Either way, we can come to a radius of 3,960 miles. So you can do it by similar proportions, right? 12 foot of drop over 3 miles is equal to a 3 mile arc length across what radius, right? So that's one triangle. Or one way to solve it by ratios of similar triangles, keeping the angle constant. Or you can just solve it by simple trig, saying tangent of 0.0434 equal to opposite over adjacent, and the adjacent being the radius of Earth. And so that's how you get those numbers, and that's kind of how I think they used our eyeballs to derive a diffraction-limited drop rate, which to me is kind of the one that's not subject to different weather conditions, kind of like refraction can be and other issues can be. This is the one where it's not negotiable, really. Right. Our eyeballs don't see better than this, and we lose this amount of information at 3 miles, bar none, for the most part. Now, when we start getting into optics of cameras, they have much lower resolution limits. We're able to see much further, and now here we have this discussion of flat Earth because we're seeing things we shouldn't see, right?
Right. Do you think that the ramping up of the horizon, or the bottom angle that we're seeing, would that make a difference when you're talking about cameras, or would they still have the same issue, or would that issue happen further out?
To me, I haven't. So that's the next part of this is I've only done this with an iPhone and kind of looked at the rate.
Gotcha.
And I wanted to do it with a Canon EOS or something like that, or a P900. I think that'd be interesting to do, just to compare the two and see. But remember, too, they're going to have different fields of view.
Right.
You need vertical fields of view, meaning that the floor isn't even going to start until a certain distance, depending on the different camera type. But to me, what ends up happening is that purple line is just, so let me go back here. Let me see. Do I want to escape? I can escape, and we might be able to shrink it down again.
Okay, go ahead, and I can shrink it. Okay, I think I'm
all right.
good. Go ahead. Yep.
All right. So let's say, how I envision this works is that this purple line right here, or these black lines, right? I can just resolve smaller and smaller black lines. So instead of like 819x, let's say, I might be able to resolve 1024x with the next higher camera.
Okay,
and
gotcha.
Maybe I get to 1500x with the next higher camera, and so on and so forth. Okay.
Gotcha.
So I can see further with better apertures. That's how I envision that working.
Okay.
All right, so we got to here. So again, this is kind of just pulling out those triangles, and you end up with two different calculations. You end up with the height loss or drop, which is this formula here, h equals r minus r cosine theta, and that's from this well-known diagram you can get off the web. And then the horizon gain, how far you can see, is a second calculation, and that's equal to 1.22 times the square root of the height in feet, as far as is how far you can see in distance in miles. And I just showed, this is the Wikipedia page where it shows that that's what the formula is. Anyway, that's just kind of a gee whiz, I guess, point. The second part of this, I guess, is just 8 inches per mile squared and kind of how that works out. 8 inches per mile squared works out as a parabola. It doesn't really extrapolate back into a sphere if you just start plugging in numbers and distance. It seems to be very accurate to about 100 miles or so, and then it kind of starts to break down a little bit. But for the most part, none of us are seeing beyond 100 miles unless, you're kind of,
right.
Doing the infrared stuff or whatever. But most of us are seeing, although, that world distance photography, that was like 200 plus miles, right? So
yeah, usually those happen around sunset or sunrise when you get basically a silhouette of a mountaintop. It takes the sun being behind it, because I don't think any mountain at that distance can resolve itself. You're not going to see, for instance, Canigou, the mountain that can be seen from 175 miles. It wouldn't resolve in your eye. The only reason it does is because the sun gets behind it, creates a silhouette, and then we can see the silhouette compared to the background sky. So I think that's why some of those distance records are found. But you're right, you're not going to see further than 100 miles unless that happens.
Right, or unless you have the aperture that is allowing you to see those small angles at farther and farther distances. So
possibly,
like a
yeah.
telescope or something like that has a huge aperture and can gather all those wavelengths of light, and they're not getting diffracted, and image integrity isn't getting all jumbled up. So the 8 inches per mile squared issue, essentially what they do with this is they take this purple line and they kind of rock it across a horizon, right? So if you increase your observer height, you can see more of this this object down to its base. And if you lose your observer height, this purple line gets kind of rocked upwards. So essentially they take this curvature rate across a parabola, and they add in factors of observer height and object height. So easily, if you think about it, what they do is they just split it down the middle between, if you had if the object height and the observer height are about the same, you can just take 8 inches per mile squared and you can cut it in half, and that's essentially what the loss rate is going to be. But so leaving that just for the moment, again, this is kind of speculation as to just how we got to this point, in my opinion. And what I also wanted to impart here is that this is the other thing that kind of threw me. I'll show you the one thing that proved to me anyway that we lived on a flat plane. This is the second thing. So the second thing, the first thing I'll get to later. The second thing is that I saw this Earth curve calculator, okay? And I'd never seen this before. And then when I saw it, it just clicked that this is not right, okay? Because you have this person leaning backwards, staring across a bulge that's supposed to be the center point of your vision, looking at another object leaning backwards on the other side. Okay.
Right.
So I don't care that you can't see the tilt angle. I'm just looking at this and saying that's not how vision works. This bulge here in the middle is not a physical bulge, right? That is always at my midpoint of vision. So, because if I increase my height, and let's say I kept everything stable, my head is stable, my feet are stable to the ground, and I just move up, let's say 2 feet in the air, I jump up, right? What if the horizon is truly a physical thing, right? Unmoving part of the earth, what should this purple line do? It should move up with me, right? As I jump up and down, okay?
Right.
It shouldn't rise to my eye level. That's why this whole issue of the horizon rising to your eye level is such a key thing, right? Because it tells you that the horizon is an optical phenomenon.
Right.
The horizon is not a physical bulge of earth that just happens to always be at the midpoint of vision, such that as I increase my height and I'm looking at this H1 target, this red arrow here, I have to bring my vision down in order to continually see it. It makes no sense to me, right? You don't bring your eye down to the ground continually as you move up in height. The ground rises to eye level. Does that make sense?
Absolutely.
So let's move back to the perspective a little bit. So what about this loss rate gives the appearance of curvature? And we kind of delved into this a little bit just by how perspective works, how this ramping, you can see how this halving effect by itself could potentially lead to the false impression of a curve, right? These dual parabolas here.
Oh, yeah, absolutely.
So again, we talked about this earlier. The color-coded lines can be represented as just 8-foot objects, right? Because the ceiling to the floor is 8 feet.
Right.
And so this red line and this red line is 8 feet, and they all color-code back to that 130-foot part. So what I want to impart here is important. So perspective represents our linear world by coupling exponential height change with exponential distance change. So just because, so you see how this is moving kind of down as a curvature rate, as an exponential function, right? Mm-hmm. But what you're not really seeing is how the ground is compressing towards you exponentially as well, right?
It's the same. Mm-hmm.
So because that's how you get to this point where it's linear, such that you can double the distance in half the size of an object, because it's an exponential height issue and an exponential distance issue. And when you couple those two together, you get a linear relationship between the two. Okay? So if you are to disregard one of those aspects, you would erroneously extrapolate a curved surface. Okay? And so that's what I'm showing here. So if you were to take any double the distance phenomenon, like this guy he's a certain number of pixels, that's what I'm showing with the P here. And I move him he's 219 pixels. I move him down to 106 pixels. He goes half the size. Well, that occurs from 20 to 40 feet at 2x. And you just keep doing this, right? Double the distance, half the size. That's all you have to know for this part. But if you were to scale this orthographically in kind of in Muppet vision, right, from a side view, and you were to say to yourself, well, he's 1 mile, he's 2 miles, he's 3 miles, he's 4 miles. That's from 1 to 2 is the same as 2 to 3. It's the same distance, right? So it should scale this way, right?
Right.
And you were to map this out, and you were to just say, well, what's the height difference between these two guys in angular size? Well, you would erroneously extrapolate this curve phenomenon, right? Because you're plotting something as a semi-log function, right? You're only using one side linear and one side, exponential, logarithmic. So what you really need to plot this as is the log-log plot, right? So if you ever look at log paper, right, it's going to compress on both. A log-log paper is going to compress on both axes, right? Semi-log paper is only going to compress on one axis exponentially, on the other axis linearly. So this is another way I think they might have erroneously extrapolated the curve, is not realizing that not only does this guy diminish in size exponentially in this way, but his distance also has to be compressed exponentially, okay? Because you have to maintain that linear relationship between the two. And when you do that, you realize it's a straight line. If you don't do that, you can erroneously extrapolate out a curve.
Right.
So I was just thinking about that the other day and kind of messing with this whatever you do to this side, if it's 1/1 squared, 1/2 squared, 1/3, whatever I do to this guy exponentially, I can't just do that linearly here. I have to square it as well. So this is 2 squared distance away. This is 3 squared distance away. This is 4 squared distance away. Okay? So anyway, I thought that was kind of cool. But whatever you do to one axis, you got to do it to the other, or else you're gonna falsely derive some kind of curvature issue. Because that's how this. I mean, just look at how perspective does this, right?
Right.
You almost see the curve within just this is a flat hallway. Remember that, right? I took all these measurements from a flat hallway. So, all right. So the other thing I just wanted to say here, and this is kind of cool, is that we talked about this earlier, is that much of the information that you're seeing is very little actual total distance.
Right.
So if 86% of the total horizon distance is contained within these 3 compression rates, which are just these 3 lines right here, which are all right there. That's 86% of your distance vision, okay?
Wow.
Is in those 3 lines versus only 0.05% of the total horizon distance is 1/4 of the image, right? Or 1/2 of the lower field is taking up just 0.05% of your distance vision.
Wow. So if we're seeing the ocean to a 3-mile distance, the horizon's at 3 miles, you're talking about the actual amount of ocean that you're seeing in that first 50% is tiny compared to the whole.
Yep. So that's perfect. So thank you, Jaron. That was a great segue. So I don't think you knew that, but I was at the beach the other day, and I decided just to take a picture I was at a 6-foot observer height roughly, and so I took a picture when I saw a bunch of cresting waves out in the distance. All right. And so I tried to time it where I saw a cresting wave, and I just chose this one. So I blew this image up right here. You can see the little tiny white dot. I don't know if you can see it on your screen or not.
Probably not.
But it's this little white thing right here, and I just blew the image up. Can you see it when I have it blown up?
I can. I'm not sure if the viewers can, but it's there.
All right. There's a little white cresting wave that this arrow is pointing to. Okay, so how far is that cresting wave, right? So you apply the same formula to this, right? So from a 6-foot observer height, I know from these hallway examples at least how much, and this is the same phone or same camera. So I know that within this visual field, I'm compressing, 9 feet worth of information, and it goes up from there, 18, 36, 72, 144, so on and so forth. So at what line does this cresting wave hit, right? Well, it occurs at 128x. 128x is about half mile away.
Wow.
Right? So this cresting wave up here, that right there is just a half mile away. And I still have 2.5 miles that are pressed between my pointer and the horizon line.
Right.
So you have to think about that. That's how perspective really works. Right?
Absolutely.
So,
yeah, well put. I think people will clearly understand that.
So this wave crests at just 120 or just a half mile away for a 6-foot observer. An additional 2.5 miles is compressed between that wave and this purple line. That's 2.5 miles. That's the majority of your vision. So,
and that's blown up too. So people have to realize that it's not,
right. This is the non-blown up version right here. You can barely make out the line. Right.
Absolutely. Yeah.
I had to press that line down into like a half point pixel or whatever it is. All right, so these are these light disappearing examples. And so what I want to try to transition to here is now kind of small obstructions, and how when we have this ramp rate, you can have an uneven floor, and such that, let's say one tile, is maybe a little bit raised here. Mm-hmm. That could completely obscure anything down the road.
Right.
So that's one particular, reason for why we have this phenomenon. But to me, the other reason is just that I'm moving the visible world in closer as I get closer to the ground. It's moving closer to me. My horizon line is moving closer. And so everything in the distant is going to set. And I think if you watch closely, you'll see this distant wall, kind of where the crack is below the door, and this kind of this matting here along the wall. Mm-hmm. You'll see it kind of set as a whole. Right? It's not like it's like some uneven floor or linear obstruction issue. It's like it's linear across the whole wall.
Right.
Okay. So let me see if I can play that here. I'll blow it up here so you can see it. There's the light disappearing right there, right? Light appearing. So we've seen that before. Here you can see it in slow motion. The light's gone, and I still have a couple inches to go, right? Not just a centimeter to go. It's a few inches, right?
Wow. Yep.
So let me see if I can. We'll just watch this. You see how the whole thing almost sets that tile in the background? It's like the
you're
whole
talking
thing
about the
sets,
entire baseboard.
like the entire wall. You know, let me play it one more time and see if I can. But yeah, to me, the entire wall is like setting within the lower visual field. You see it, right? Like you're just seeing.
Yep.
It's a little blurry, but that to me is that phenomenon. So,
which is why we're losing that light. And what are you using down there? Just a flashlight?
Yeah, it's a pen light,
yeah,
basically.
Okay.
So it could be small obstructions in the foreground, but to me, I think it's an example of that lower floor horizon being brought closer to the observer.
Sure. Yeah, but I mean, if you laid a blanket down on that floor, even if you press that blanket as tight as you could to the floor, I mean, you're going to lose that light even quicker. And that blanket may be all of, quarter inch high. It's just simply going to block it even sooner.
Yeah, exactly. So I'm going to try to move through this because I know we're getting short on time. But let's see. So this is just kind of the light examples. I'm just moving myself lower, and you can see how the buildings change, how they ascend to this purple line a lot sooner as I lower my eye height. And that's all I really wanted to say here. But then I wanted to relate it to the beach, right? So now instead of a flashlight, it's a cruise ship, right? And it's moving away. So the same phenomenon is essentially going to occur. A small wave right here could be obstructing this, or my horizon is only a certain distance away, and this thing is already ascended to my purple line within maybe a half mile away, right? That cresting wave was right here already, right?
Right.
And so this cruise ship, just a half mile away, or let's say it's a mile away now, it's already riding on top of this purple line, right?
Right.
So what happens with further distance? Well, it's just going to descend within perspective and set, So,
and more and more of it would be obscured by the closer ground.
Yeah, or a small wave,
right.
Like here at a quarter mile away or half mile away, could completely obscure. As this thing got a smaller and smaller and smaller away, a small wave right here could just kind of move above that purple line in your visual field for whatever reason,
right.
Totally block what was further out.
Right, which we see this. I mean, if people have looked at all the videos of the ocean waves, if you're looking across, you can see that crest of water. You might call it swell, whatever you want. You can see it move up and down, which clearly tells you that what you're seeing is much closer.
Right.
Otherwise those waves would be 50 feet, 100 feet tall. We know that's not true.
Right. Yeah, they're just closer to you. They can be much smaller if they're closer.
Have you seen? I'm sure you've seen a lot of the work that Zachary Zabal has done. I mean, Good Times for All, right? He's done some great work. Make sure you guys check out his channel because he's got some stuff he does in a warehouse where we can see exactly this, the ramping up of the floor when he's close to it, and then he's got a bunch of these little black boxes or canisters going down the whole way, and after a certain point, they start to drop behind the horizon line that's built basically as a result of the camera's height from the ground. Go ahead. Yeah, no, I think Zach deserves a lot of credit for that because I think, and I don't know where this diffraction issue kind of originated. I really don't, but I know that I think Nathan kind of got it from Zach, and I got it from Nathan. Right. And so, because I know Nathan was really pressing this, and I was like, man, what is he talking about? And I had to go look it up. And as I started to look into it, I was like, holy crap, this stuff is trippy stuff, Yeah, it's trippy because once you realize that the horizon is optical, which I totally think you've already proven here just already, and everything that I've researched and seen has shown that to be the case. If that's true, then the fact that our eye can only resolve things at the exact rate that matches this so-called sphere that we're said to live on it's actually simply impossible. I mean, really, it's impossible. There's no way that just matches up. So, and I've been asking people forever to try and prove to me that the horizon line is anything other than optical. I have not seen anybody provide any kind of evidence for that. I mean, if it was true, I've talked to people before and said, if you're on the moon, just as an example, let's say that there's a small sphere in the sky called the moon that you can go to. And I've said, what would happen with railroad tracks on the moon? Would they not reach a point, but would instead reach the horizon and kind of fall behind it? No, the answer is railroad tracks on the moon would do the exact same thing they do on Earth, which is it's an optical effect. They meet at that horizon point, at a point, at the vanishing point, right? So that right there tells me that it's an optical effect. This isn't a physical effect. The railroad tracks don't get to the edge of the sphere, and it just so happens to be the place where they become a vanishing point and disappear.
Right.
It's ridiculous.
It just so happens to be the point where they also converge left to right.
Right.
Yeah.
Yeah, it's just simply impossible. So, and this is great while you're giving this presentation, and I still think people miss this point because it's probably one of the biggest points in this debate. So, yeah, please continue.
Yeah, I think when they say when we say perspective is not factored into the calculator, people get all up in arms about it. But the problem is that perspective, this horizon, this center point here is just the center of my convex lens,
Right.
It allows the floor to meet the ceiling at a certain point. And so if you're saying that this is now Earth curve, well, we have a problem. We have a disagreement of what's going on. So
right.
That's why we say it's not factored in, because it is the thing, right? It is the bulge.
So my question is, and probably the easiest way that I could prove this to people, and I'll have to ask you because I'm not sure the answer, but if we have a tunnel, and let's say we have a 10-mile straight as an arrow tunnel, okay, and it's got no lights on the inside, so if you're standing at one side of that tunnel, I don't think you'd be able to see the light at the other side of the tunnel. You're 10 miles away. The ground's going to ramp up. The horizon line's going to be created before you ever see the other side of that tunnel. My question would be, if somebody pulled out the very best telescope that there is, would that change? Or
right, that's the question.
That's the question.
And I have that same question. So I think they would, if you were able to get the resolution down to a sufficient amount. I think they would. The calculation, I guess I could do that. I don't have my phone with me right now. I have to do the calculation, but you could just do it by whatever that angle. So let's say the light is you'd have to determine whatever the light size would be, the radius of the light.
Right.
And then, but again, there's other issues. So here's another just caveat to this. There's other issues just besides Rayleigh criteria that allow something to be resolved. There's also focal distance issues. There's brightness of the field. There's a lot of different things that are different. There's different calculations for resolution. So when people say, oh, it's just the wavelength of light divided by the diameter of the aperture, that's not necessarily true. There are other issues that go into whether or not we can resolve something. So
okay, gotcha. That's something
that's
something we can work on. If we make a couple examples, maybe I'll make a video about it because I think that's hugely telling. People tend to think that when they say, well, on a flat Earth, wouldn't we be able to see forever? Wouldn't I be able to take this telescope and see the sun on the other side of the Earth? And really, I don't think you'd be able to take a telescope and see a light on the other side of a tunnel. So, I mean, when we're talking about 10 miles, let alone when we're talking about a sun that's some, 8 to 10,000 miles away. But go ahead and continue. We'll do that separately.
Yeah, no, we're diffraction limited. And so they'll say, like, well, I can see a star. How come I can see a star that's 80 trillion miles away?
Right.
And you're like, well, because you're not seeing 80 trillion miles away. The star isn't that far. Hate to break it to you, but that's...
Unless you make the stars super gigantic and super far, and it just gets into nonsense after that. But go ahead, this stuff's great.
So here I have this Walmart example again. So again, I just got really close to the floor, and you can see now how the floor is essentially my lower 50% of vision, and how it kind of widened out. This red line is kind of where the corners of the floor are, right? And how they've already approximated this purple line just by lowering my height.
Right.
So if I were to remove these obstructions, right, and let's say this Walmart was now wiped out by a tornado and it just left the sky, right, I would still be at my height, right, and doing this. We already did this, so I'm not going to do it quite again. But now if I replace the floor with crops and I just stand up, this is what I see, right? So the same phenomenon where the flashlight disappeared in this example, the boat disappeared in this example, now I got a tractor in this example, whatever it is, they all are going to disappear at a certain point over this horizon.
Which proves, concretely really that we're talking about an optical effect. It's the way we see, and it works in every issue. It's not just an outdoor issue. It's just simply when we're inside or in a hallway, we've got walls and things to contain that view. But you're right, you can just wipe them away or picture them being unfolded backwards, and you're going to end up with what you see here, a line of a horizon line.
Right, to see how vision does this. So I'm comparing the walls to this red line right here, right? This is the orthogonal line
Okay.
along which I've scaled this particular image. So this is like at 2 feet high, or yeah, 2 feet high. Now I go down to 1 foot. See what happens to the red line, right? It gets it starts to approximate this purple line. Now I'm going to go down to 1 centimeter or a couple, like an inch or whatever it is off the ground.
Right.
Now the red line is essentially, because it's just how our vision works. As I get closer to the tangible surface, it's taking up more of the field. These lateral obstructions they're not as much of an issue anymore. If I were to remove these walls and just stand up, again, I see a horizontal vanishing line still. I have no walls to compress my vision inward. And so I see something like this, right? I see something like this. So you don't have walls pressing your vanishing point inward. In this case, you have the crop lines. So my blue lines are off a little bit in this photo. Let me see if I can fix it. But you have these crop lines, which are kind of showing you your orthogonal lines, these potential lines. Mm-hmm. So if I were to put a building now, instead of building down, right, it would press along wherever that building ended up being. Let's say it would, be right here. Then these crop lines would now just be within a building, right? I remove the walls and now I blow the building away, and now I'm left with more and more crop lines, and it just extends out to a horizontal vanishing line. Anyway, does that make sense?
Absolutely. Yep, I get it.
It's just how our vision works. We don't have tangible surfaces compressing information. We're going to extend it out to a horizontal vanishing line. So here's the small obstruction example. So I'm only going to do a couple of these, and then refraction, then we'll finish up.
Okay.
So we talked about how this ramps up quickly. So this is this ramping up phenomenon, this red line, right? It ramps up quickly, and then we have this long plateau period before we may even see where the distant object is. So in this case, they don't have golf balls in Keynote, so I had to use a baseball. But this red line is this kind of ramping, and this purple line is now my plateau period, okay? So red line is still ramping, and then I have this plateau period within perspective.
Gotcha.
And now if I were to have a small obstruction, say this size right here, this little blue triangle, how big does that have to be to completely obstruct this ball at 130 feet away?
Right.
All right? So I'm assuming now, I have to assume that I've lost some information of this golf ball due to diffraction. In other words, this has set a certain amount because it's greater than 95 feet away. I determined that my horizon distance at this particular height, which is 1 centimeter, was 95 feet away. Okay?
Right.
And the way we did that was that calculation earlier. All right. So assuming that I'm now looking at something beyond 95 feet away, 130 feet, it's going to have set a certain amount. And the amount that it's going to set is 0.55 inches worth of information. And the way you calculate that is just you take your distance to the object and you multiply it by the resolution limit, and you're going to get a loss rate. Okay? Beautiful. So this is the loss rate. I now subtract this loss that I think this golf ball has set a little bit within the field to get what the remaining amount of golf ball is above the purple line that I should be able to see. And so I come out to 1.13 inches. So let's just say that that's what I'm looking at, 1.13 inches worth of golf ball, because I've lost a little bit of it. And if that doesn't make sense to you, just disregard that altogether, and you can just use 1.68 inches. It doesn't matter. But that's how I calculate this out. So you can use similar triangles here. So because I know this angle is the same between this half of the golf ball and this purple triangle, or this blue triangle, right? It's all within the same yellow angle, right? So I can just use similar triangles to see whatever the height of this obstruction needs to be to completely obscure all of this information within this yellow triangle. Does that make sense?
Yep.
Okay, so they just use ratios. So for this particular case, I use 1.13 inches because I assumed 0.55 inches is lost from diffraction. And so I end up with this 1.13 amount. That's this top number here. So that's going to give me, and that is the object across 130 feet. And it's going to equal X amount of the triangle across 30 feet. So the example is, for a 1 foot or for a centimeter off the floor, how small does an obstruction have to be 30 feet away to obstruct the bottom half of the golf ball 130 feet away. That's my example. Okay. So the answer is 3 millimeters. Okay. So that's crazy, right?
Wow.
That's a really small amount to obscure just the bottom half of this golf ball. But if you look at this image in perspective, you could see how something right here, 3 millimeters worth possibly, or let's say even 6 millimeter, maybe a centimeter worth, right? Up to about yay of this golf ball would totally, you can't even see that golf ball.
Absolutely.
Right?
Yep.
The light is like barely visible in this photo, and the golf ball, I can't even blow this thing up to find this golf ball sometimes. It's like a dot back here. So that to me, so now I just take this and extrapolate to other examples, right? So now I'm going to say, how tall does something have to be at 60 feet away to obscure something 360 feet away that is 0.4 inches worth of light, right? So now I'm going to say this light was obscured from a small obstruction in the foreground. How big of a small obstruction? Well, if you do this by similar triangles, assuming that you're on this plateau region within perspective, it's very small, right? Because things get really tiny at 360 feet away. But things at 60 feet away,
right,
they have to be quite as small and to completely obscure that thing in the foreground. So, and then you can take it for a ship example, and you can say, all right, given a 6-foot observer with 1 arc minute of resolution, how big would a wave have to be at a quarter mile away? Now, I probably should have done this at a half mile or even a mile, right? But I did it at a quarter mile, and I probably should, because we saw that cresting wave was at least
about a
mile. So a quarter mile might be like somewhere in here.
Okay.
So this one, I might need to modify this one a little bit, but the take home message is that let's say it's a 3-foot wave, right? I said a 1.5-foot wave would obstruct the bottom half of the boat, but so let's say it's a 3-foot wave. A 3-foot wave would obstruct the bottom half of the boat, right? So a 250-foot tall boat. That's 20 miles away.
Right, and that doesn't even bring into account if you want to start talking about swell, which the swell is often, double digits feet, and you may not be able to see that from the shore, but it certainly would block if you're talking about a swell that's popped out a half mile. Think of how much that would cover easily a 250-foot boat, 20 miles away. But go ahead.
Right. And I think Ranty's kind of brought that up recently too about something called I think he brought up recently. It's a barotropic tide phenomenon where there's all these swells within water currents, and underneath, there's different temperatures and different things that cause these bulges within water.
Right.
So water levels can have kind of an uneven surface to themselves, just like possibly a floor could be uneven.
Correct.
So, and so then we get into that hopefully that's from just kind of a physical standpoint of like how a small obstruction could obscure something further away, because it's just, again, we have this plateau effect within perspective, and things ride along this plateau for a long time before they actually start to kind of set and move away. So something small that's up on that plateau relatively nearby, just like we did that cresting wave example, something tall enough to go above the purple line in choppy water or whatever would totally obstruct something further away easily. And it doesn't have to be a curved surface, right? So you don't have to invoke curvature for that phenomenon. That's just a normal everyday aspect of vision.
Right.
So Dr. John D, I know you're aware, so he's done some great stuff, and I got a lot of my refraction stuff from him, and kind of how he's done a lot of these, and you've done a lot of laser stuff too, where and I don't know if this is maybe what happened when you did your experiment, or you saw that things got obscured, or whether or not the bushes were in the way or whatnot. I don't know, but it's possible too that because you were near now I will say that body of water is relatively small that you were next to, right?
Yeah, for the most part.
But I don't know, I think the water emits, in general. It does absorb a little bit during the night, but for the most part, water is an emitting thing. It has a large specific heat, or it has the specific heat of water allows, the trapping of a lot of heat. And as there's a great, if you go to the Metabunk 7/6R discussion, there's a lot of contradictions in there, but everyone the site that the source that they cited essentially says, oh yeah, well, water emits during the day. It actually makes the air above the water a little less dense. And you're like, what?
Oh,
Wait,
boy.
back up. You can't be admitting that, right? Because
Right.
you just blew the whole argument out of the water, so to speak. So anyway, the point is, I think for the most part, upward refraction is the standard. If you were to say that there was a standard refraction, I say that in general, the optical density of something increases in height. And I think we're kind of coming to terms with that with some of these observations. So that's what I kind of want to bring into next, and I'll try to get through it as quick as I can. But this is from the Stephen Hawking episode, right? And so I know you've seen this before, where they have the boat and the 3 mile laser, right?
Oh, yeah.
Okay, so and he goes to 3 miles, and he's like, oh, look, it just happens to be 6 foot above, above the water surface,
Right.
not taking into account the fact that this laser is like a good 1.5 feet at least off maybe 2 feet above the water level.
Yeah,
so
I think it's 2.5 feet. I think they have it at 31 inches, and they never level it to start with. But yeah,
Right.
Go ahead.
No, it's full of holes, but
Yeah,
but what you can see here is, if you go back to Dr. John, so you can see how you can see kind of this upward refraction phenomenon. So during this video, I caught this kind of same effect going on, right? For a split second within the frame. So I freeze captured it or whatever. And but to me, this is just upward refraction. So their version of what's going on in this thing is that the earth is falling away from you, right? The water is bending
right.
down, right? And this boat has sunk down across the water. This laser is straight, and that's why it's risen up, right?
Right.
But the reality is that the laser was refracting up across this body of water that was emitting, and the water itself was straight, right? You just have to flip everything upside down. And
Right.
then it makes a lot more sense. So I did a lot of work with refraction. It gets a little confusing sometimes to people, is what I've kind of noticed with discussions. So what I want you to think about, I guess, is in terms of a cup in water, or I'm sorry, a coin in a cup of water.
Right.
And if you were to observe that coin, where would it be, right? You often observe it higher than where it actually is, right? Because that's a downward refraction phenomenon. As that light is leaving that coin, and it travels through the water, and it hits the air, it bends towards your eye, okay? And when your eye receives that light, it straightens that out and creates the false impression that coin is higher than it is. So that's all refraction is your eye or your camera assumes straight lines, right? It assumes that the light that is reaching it is a straight line. But we know that the light doesn't travel in straight lines. It travels through these different gradients of density, optical density. And so when you come to terms with that, you realize that images can move within a field quite a bit. And so I did a lot of analysis on Red Pill's footage. He has some great stuff, and Ranty has some great stuff. And even I threw in some Soundly stuff. So I'll kind of go over that quickly here. The main thing is that if upward refraction is a phenomenon, and I think it is the primary standard phenomenon over water, especially during the day, then all of these effects, to me, are examples of that. Bending bridges, bending power lines, compression of floors, images being brought a little bit lower than they naturally are all examples of upward refraction. And so when this upward refraction is somewhat gradual, then the compression of those aspects is gradual. If it's abrupt, right, so I have this density gradient really rapidly diminishing, well, then you can get this differential floor compression phenomenon. And Ranty's shown some boat compression issues. And this kind of compression issue, to me, is just a rapidly dissipating optical density, or rapidly increasing, let's say, right? It's increasing in density.
Mm-hmm.
In other words, the air above the water is a lot warmer than the air as it moves up. And we know that to be the case, right? Temperature does get lower with height. And temperature is by far the largest factor within refraction. So this is from Ranty. So Ranty, he did this somewhat inadvertently, but what he did was, on one day, he was capturing some footage, and he just, from a really quick point in time, he went from a 4-foot elevation to a 9-foot to a 14-foot elevation, okay, within a very short amount of time, all right? And on another day, he was doing a time lapse from roughly the same area, and he set his camera down at 4 foot, okay? And he just let it roll for, I think, 2.5, 3 hours, and the tide was coming in. But what you see and what I did with the yellow lines is I'm just doing the center of frame. Where's the center of frame for his camera?
Gotcha.
And I standardized it to the corners of each. You can't see the corners here, but they're put to the corners of each frame, where you can get the central vanishing point of each frame. And so you see this mirror line, horizon line, right, or this inversion point is low over here, and you have X amount of lighthouse right here, right? And throughout the day, as the water is, you get kind of less upward refraction phenomenon occurring. That's what I think is happening anyway. This thing rises to a more stable position, and it's lower when you have more upward refraction to begin with. So the reason I say that is because, so if you look at these two images, right, the 14-foot elevation is almost the exact same thing as this 4-foot elevation at 9:30 a.m., right? This 4-foot elevation is the same thing as this 4-foot elevation at 10:15 a.m. This 9-foot is the same, right? See, the entire image was brought up throughout the day,
right?
So, and you can see the lighthouse here. The lighthouse, the mirror inflection, the inflection point kind of is down here, right? And here's the yellow line. And as throughout the day, it gets higher within the frame. So, so Travis from The Plain Truth, he just did this one recently, and I thought this was awesome. So he did a still, and this is also a time lapse. The camera's not moving at all, right? It's set there. It's not moving. He takes a still shot at a certain time frame and then just watches this thing move. And so when you look at his video, and the link will be in the description, you'll see how this entire thing moves downward within the frame, right? And so this is him just taking another still shot, or this is actually, I think of me, I still shot at his video at this point when it was low down, right? So you can see how an object bodily moves just from refraction phenomenon within a time lapse, right? And look at this one; it's even more dramatic, right? So this was a still shot when he reoriented his camera, and then he allowed it to time lapse as it went down, right? And this one went all the way down here, right? So just show. Have you ever seen the Skunk Bay footage, the Skunk Bay time lapse?
Oh yeah, definitely.
Right. So you can see how just throughout a day, like, stuff can move a crazy amount. So for anyone to to say like, oh, I made this observation over water and look how much is cut off, and that's and how much is visible, and that's proof of X, Y, Z. That's crazy, right? You're just taking a snapshot of a point in time. If you were to sit there and set your camera up, you would see the amount of refraction that's going on.
Right. So
this is some really cool stuff here. So Red Pill, I encourage everyone to look at this video. So in early January of 2019, and he'd been taking this footage of this condominium for several months, right? And he's trying to get this lighthouse, but he just so happened to pan over to this condominium each time in each of these times he went out. And so what I was able to do is I was able to grab this nearby tree line and standardize these images against one another, right? Because he had roughly the same observer height for each one of these times he went out, okay? Right. And so in January, he caught this footage here, which is this third image over. And you can see where the apparent horizon line is, roughly 6-foot observer across the way. And the reason I say this is because it's also this image down here. So I just drew my purple line. It's roughly where his height would be.
Gotcha.
14, 15 miles across the water where this condominium complex is. And so I was able to use that as kind of a standard, and as, compared to this tree line. Now, how do these other images on these other days stack up against that, right? And so what you end up seeing is this entire complex has different positions. And what I'm doing here on the right is I'm just blowing this thing up sequentially, keeping the heights the same, okay, across each image, right? So that the purple line is the same across each one, but you're seeing more and more levels of zoom. So this fourth image here is the next day, the very next day after he took this awesome footage, he went out and he took this footage, right? And you can see all this inversion going on, right? You see all the mirroring going on. You see where the top stacks of the condominium are now,
yep,
compared to the tree line. They're dropped immensely, right? So, I mean, look at this image here, right here. See where these stacks are, and now compare it to here. Totally different images. So what that told me was that on the best days, when you see the furthest and you have the best resolution and the least compression of these floors, right? This floor compression issue, this miraging issue, those days your horizon line is going to be higher, not lower. So for there to be a downward refraction phenomenon, you have to assume that this is actually the correct image and this is looming. This third image here where you can see for miles and there's no compression, there's no mirroring, it's undistorted, right? That's actually the false image. That's the looming image. This is the real thing, right? And that's not the case. If you know what I mean? Mm-hmm. That's absurd to me. I don't find images with true looming. All I find is horizons are the highest with the best resolution, and they get lower from there. So, does that make sense?
Absolutely, it makes a lot of sense. First, I thought you were saying that was the loomed image. I was like, I don't know about that, but I see what you're saying now.
That's what I'm saying. That's the counter argument.
Right.
Counter argument is that has to be looming, and you're like that's a perfectly clear image. That's an awesome image, you know. So, and if you look at it, I guess I don't know if I have it zoomed out. There's one where he has this thing zoomed out, and it is a perfect day. And I looked up the temperature when he did this because we were talking about it when he shot it. The water temperature was exactly the same as the air temperature that day, both 70 degrees. And the water was perfectly calm, and you could see basically the clouds reflected in the ocean, like all the way out. It was just a perfectly calm day. The water and the temperature and the air temperature are exactly the same. He saw for miles. So it was a great day. And I have other footage on that where I kind of compare how much is getting dropped when diffraction actually does start kicking in for that image, and it comports kind of perfectly and linearly, right? So anyway, you can check out that. That's in part 4 of my video series, and you can check out Red Pill stuff. It's in the video links in the descriptions. Really quickly, the Lake Pontchartrain stuff. So you can standardize these power lines with an orthogonal line, right? So you can look at this point along the Pontchartrain power line, and you can look at this one and this one and this one. So you can eliminate kind of height discrepancies by lining them up in this way, or at least making sure that when you're comparing two images, that the horizontal orthogonal line crosses the same point on the power line within the two frames. That's going to eliminate height discrepancy issues between two images. So you can find these online, and you can compare. One person went out and did a great image one day where you didn't see this bending. You see the bending that is occurring right here? That's not Earth curvature, right? That's just refraction. That's upward refraction. That's pressing everything in the distance downward to your eye line. Because again, your eye assumes straight lines. So this light is coming into you curved. Your eye is assuming a straight line, pressing it lower the more distance it goes. So if you blow up this image right here, you see that essentially you have a perfect vanishing point, almost a near perfect vanishing point. And when you kind of compare it to the days when you had all this curving issue, you see that the apparent horizon line is much lower. So that's just kind of a dual effect. You're seeing something bend, but you're also seeing the apparent horizon brought lower within the field. So hopefully does that make sense?
Absolutely.
It's I can get kind of so how much should a horizon drop, right? It depends on what a horizon is, and that's our bottom line, I think, here. Is it a bulge of Earth that you view leaning backward? And what happens if you jump up in the air, right? If the horizon is a physical thing, okay, not an optical thing, then it should just stay where it is, right? As you move your position relative to it. You don't have to adjust. Why
right.
Again, like I can't stress this enough. When I go up in a balloon, I don't drop my head down to see the horizon, right? Anyway, it's crazy to me. So if you say it's both, right? Or is it an optical effect of a biconvex lens? If you say it's both, well, the ceiling meets the floor at the midpoint of vision in a flat hallway. So why is that phenomenon not accounted for, right? Why is it instead assumed to be Earth's bulge within an Earth curve calculator? Why would our vision suddenly change when outdoors? So these are questions that, to me, are not answered adequately.
Right, not at all.
really quickly, here's the there's horizon does rise to eye level. I know I saw an early video of one of yours. I think you were doing with Bob, where you were in a plane, and you guys were saying that, well, the horizon did appear to drop, right?
Right, which I think is simply because we can't see far enough, and when you've got all that atmosphere in the way, that you just lose. It's kind of the same issue as you get higher up. But go ahead and explain it.
Well, yeah, I think you'll like this. So, I've been. This is the other. So this is the. I said two things kind of kicked it for me that this is a flat plane.
Right.
The second one was that Earth curve calculator. It just doesn't make any sense. That's not how we see the world. This is the first one. So when I was getting into flat Earth on my way to the cruise or back from it, I can't remember, but I taped my phone to the window, did the whole thing, and I'm like, man, it stayed there the whole way from 300 feet up to 30,000 feet. It stayed the same, right? Here we are at 35,000 feet, whatever it is, and here I am down, near the tarmac or whatever.
Right.
I'm like, wow, it did not drop the way I would think it would. So I then went on another plane, ride, and I did have it drop. And I was like, man, what's going on? So you can see in this footage here, and I standardized the kind of the frames of the window, right? And I'm like, sure enough, you can see this amount of sky here, right? And this amount of sky here, and this amount here, and sure enough, the horizon looks to have dropped, right? So it's kind of disheartening a bit. I was like, man, how come I get it on some planes and I don't get it on the others? So then I saw a video that Wolfie did where he was comparing the wingtip rise. The wingtip was then used as a marker, right, to show where the horizon was. And he was saying that that's proof of drop. Now, he said, well, wingtips rise, and I've accounted for that and blah, blah, blah.
Right.
But what he didn't really account for, and what I noticed one day when I was looking at this image again, is that look at what the markers on the wings do as you go up in height, right? Do you see what they're doing?
Yeah.
They're getting closer to you, right? So as your distant horizon is dropping, your wings are getting closer to the window.
Wow.
Okay? So to me, that's because this is bowing like a convex lens.
Right.
And if you take a convex lens like a lid, and I put it up against my burners here, you can see how a distant object, right? Let's say this is the horizon. This red line would be the horizon. It would drop, but also whatever was right here would be brought more proximal.
Interesting.
So
yep, absolutely.
It's like a dual effect. So I noticed it in Wolfie's picture too, where I put the markers when he was on the tarmac. I marked these. You can see this kind of this, what do you call it? Just kind of this dark smudge area on the wing. Right here, right? And my red arrow is kind of pointing to near where the wing flaps are.
Gotcha.
It's just below that dark smudge, okay? And now look at him when he's at 30,000 or 40,000 feet, where that dark smudge is compared to the window frame,
wow.
Right?
Yep.
Everything has been brought, that's like a good 3 or 4 feet inward towards you, right?
Right.
And so, and that's why I think you're getting this horizon drop issue. Now, my other thought was, okay, what if the wing is rising within the field of view, right? And that's why it's apparently being brought closer to you, right?
Right.
Does that make sense? So
Yeah.
I was like, what about that?
Right,
Well, so I looked up a bunch of
cool.
wing flex, videos and everything. And what you notice when you compare these two images is that the proximal wing, right, from the engine, about to about yay, does not flex, right?
But after that,
all the flex is here in the outer aspects of the wing. Okay. And that makes sense. This thing can't flap like a bird. You
right.
know what I mean? You want your engines flapping around. Most of the flex is all here in this distal aspect of the wing.
Correct.
So when we're looking at images that are, relatively close by to us, that's not flex of the wing that's bringing it, 3 or 4 feet. That's almost a whole flap length that's been completely obscured by this lensing effect. So, and I noticed it in my imaging here too, right? So here's this flat marker, and as I went up in height, it got closer to me. Okay. So that's just food for thought. I think that's kind of what's going on. I don't know which pane is flexing. I looked up the panes, and there's 3 panes to a window. The first one is usually that inner plastic one. It's kind of protective. The second one is like a middle layer. It's what's subject to cabin pressure. And then the third one is the outer pane, kind of subject to the outer elements.
Right.
And so which one is flexing? I would think it would be that middle pane. I wouldn't think the outer pane would flex as much because it would create like a stress issue for the cabin.
Right.
But I could see how this middle layer could totally flex outward, and it would get increasing in height. So as cabin pressure went up, the higher you went up in altitude, this would bow out a little bit more, create more of a lensing effect. So it would make the horizon appear to drop, and it would bring the wing proximal to you. But it's just lensing. It's not actually the horizon dropping. So that's just food for thought, I guess. I thought it was kind of cool. But
Absolutely.
my point was, too, if you don't see this effect, so this one of these times I did, you got to be sitting next to a wing, but I did it, and I'm like, okay, the wing definitely did not move proximal to me during the whole flight. Well, guess what? Then the horizon didn't move a bit either.
Right.
So, all right. One of the last issues here is this, and I don't want to get into this too much other than it's a point of contention right now, I guess, within the community is what is an inferior mirage really? I think of it as a just a very less dense area of air. That it's so less dense, I guess is not the right grammar, but it's to the point where it creates a reflection. And all that is it's something called a total internal reflection. And light is going to refract a certain amount when it goes from more dense to less dense. And this is upward refraction right here, right? When you have this less dense layer over the water, this light is refracting upward to your eye, okay?
Gotcha.
Now, as the light gets more and more shallow and the incident angle gets kind of flatter as it moves towards the observer, right? It's coming at you now at more of an angle parallel to the surface layer. It's going to reach a certain point called the critical angle. And once it reaches that critical angle, it essentially skips off the layer, okay? So instead of going through the layer, it skips off of it and returns at the same angle at which it entered. So this is called the reflected angle, and it's the same as the incident angle. And so that when it does that, it's just a reflection, and it's called a total internal reflection. So when you see this in water, right, so the water is more dense, then you have the less dense area of air above it, you'll see like the famous one is like this turtle, right? You're seeing this kind of inverted turtle in the water line. And that's because you're seeing the reflection of the turtle if you're underneath the water. But the same occurs if you have a density gradient in the air. And instead of water, it's just more dense air. The same would occur, but in reverse. And that's what I think is occurring with a total internal reflection. Or as a total internal reflection with an inferior mirage. There are other theories that it could be just the roughness of the water creating a shimmering or kind of effect. I don't have a problem with that necessarily, other than I don't like the way when Wide Awake showed he did some great footage. I don't like it just from a conceptual standpoint that this boat, as it moves away from you, this mirage actually moves up within the boat itself, right?
Yeah.
And to me, the reason is because it's getting encompassed kind of by this less dense medium as it moves away. The other point I wanted to make about this is that when you view this guy right here, right? This guy is 6 feet off the water. What is he going to view when he turns into 1 point perspective? He's going to view the water line at his eye line, right? Because that's how perspective works. It rotates the floor to meet the ceiling. So this purple line is going to have water all the way below it, even though we know there's a 6 foot gap between you and the water.
Absolutely.
Does that make sense?
Absolutely. Yep.
Right. So now I fill this gap up with dirty air or junky air. We'll call it this really less optically dense air, warm air. And now a boat's traveling away within it. Well, what we would see in perspective is the same thing. This purple line is still going to represent the water line far away, right? And this boat's going to start to actually ascend within this layer. But it's just ascending within water. It's not floating in air.
Right.
Okay. So I hope that makes sense.
Absolutely, yeah. Talked about that many times.
To me, it gets enveloped within this layer as it moves away. So you see where the mirror line is on this boat is kind of down when it's close, and then it gets a little higher on the boat, and then it's a little higher on the boat. To me, it's because you're moving. It's just the refraction layer is a little bit less towards the top, or this reflection issue is is a little bit less towards the top aspects of objects than it is towards the bottom, and because it's a little bit more warmer near the bottom of the air than it is as it moves up in temperature. That's the only thing I can say about it. People, feel free to make up your own opinions on what you think the inferior mirage is. I don't really want to get into it more than that because I don't know that it's a super critical point. As long as we agree that the purple line is going to have water below it. Now, I know some people have said that this blue line, where the apparent water line is, where you can still see water, is the horizon, and that this is dirty air that's just blocking what you normally would see on the boat.
Yeah, no,
I don't think so. That's the case. And here's the reason, is because where is this blue line within perspective, right? It's actually really close.
Really close, yeah. And if you're looking at 3 miles, it could be a mile away.
That's exactly right. So we did that example with the cresting wave.
Right.
And I've done the calculation I took a bunch of inferior mirage photos and kind of looked at, and when they were zoomed out, where that line actually is. It's very small, but it seems to occur within about this 128x to 256x compression area, all the way up to the purple line. So again, it's almost like that cresting wave zone up to the possible horizon line is where the mirror line occurs. And again, if you think about that, that's going to be at the most that's going to be less than a mile away. So that's not your true horizon line. That's a close thing. The last thing to wrap up here is just I did a calculation for reversing 7.6R as upward refraction. So I'm going to leave this up. I'm not going to go through this right now. Okay. But people can screenshot it if they want to, or they can just look at the video and kind of see how I derived it. Essentially, all I did was, this is how a 7.6R is purported to be. Think of it in terms of 8 inches per mile squared, right? So I took that 8 inches per mile squared as your curvature rate across a short distance, and that your height, your observer height, and your object height are roughly the same, and I just flattened this curve out, okay? And I said, well, now it's actually light bending upward at the same rate across a flat plane, instead of light bending or light moving straight as though you were on a 7/6R less curvature rate of Earth, okay? All I did was I just took the same assumption and I flattened it out. And so when I did that, you come to a formula of 0.277 feet per mile squared, okay? Recall that, the 8 inches per mile squared is 0.66 feet per mile squared. So right. This is 0.277 feet per mile squared. And you can do this for a ton of different heights. It works the same. The reason it works the same is because for every 6 foot worth of whatever your height is, you're just reducing this clock tower as 6 foot intervals all the way. So as a whole, it's still going to compress at the same rate.
Exactly.
And so observer height doesn't really come into play as much with this formula. But what's amazing, and I also assume that they didn't know about diffraction loss, and it was included in whatever they used to get 7/6R refraction. And I've tried to find where they got this from, other than, it's 14 to 16% refraction rate. Well, of what? I'm assuming they did observations. Okay,
we hope.
Otherwise, I can't find where it's from. So I'm assuming it's from observations and looking at how much of something was cut off, or in their opinion, brought up, loomed up,
right,
more than it should be, and then that's how they got this 7/6R. So I take that as they actually did the opposite of what they should have been. It wasn't being loomed up; it was being brought down by upward refraction. So when I make that assumption and I get this formula, then we can analyze a lot of different contentious things that are brought up in the forums a lot. So this is an example of the Kima Lighthouse in Texas. This was the links are in the description for all these folks. So when you do this calculation for this, you can see if this is being upward refracted and brought down lower within your visual field more than it should be, 84 feet are missing. And if you do a blink test, which again I don't encourage, but if you're going to do it, you find that that's almost exactly the amount. Each one of these stripes is 20 feet. So if you do it for the CN Tower example, So again, it's 275 feet missing for this particular image, because this image is always shown as well. Like, how come the bottoms are missing? Well, Rogers Center is 282 feet. We're different by 7 feet, right?
Wow.
Blackpool Tower in England, 30 miles away. Same thing, 264 feet should be missing. Blackpool Tower is 518 feet. It corresponds to roughly half the tower. That's how much we're missing. Possible loss for the Willis Tower, same thing. This one was seen across 55 miles away. Keep in mind, so I know you have this for, it's not a mirage, right? All that stuff. Keep in mind, you shouldn't see any of this.
Right.
Right? That's the point.
That's the point.
So,
yeah. Maybe people fail to see that or realize that, right. And I always hear
they
people
get
saying
caught up with all this, like, how come you can't see the bottom?
Correct.
But you shouldn't see any of this if the horizon is a physical thing. So I just reversed the calculator and made it upward refraction instead, assumed a flat plane, and you get a much different formula and a much more reliable calculator, in my opinion.
Seems accurate.
So 837 feet is missing across this one. It does start to break down, I've noticed in some areas. So the more distant the thing, the more refraction is going on, the more the formula breaks down a little bit. So this is the last one here. This is Conspiracy Cats one about the Mount Rainier Peak versus Mount St. Helens. I don't want to go into this. I know we're getting late, but the main thing here is that whether or not this is a perspective issue alone or a refraction issue. And I kind of go to the point where I don't think it's a perspective issue, because Mount Rainier is twice as big as Mount St. Helens and is twice as far away. It should be roughly the same angular size. And so if you were to reduce your height all the way down to sea level or the base of the mountain, these two blocks, right? If the yellow block is twice as far as the gray block, but in orthographic view, they're exactly the same size.
Right.
Angular size wise, this yellow block is actually going to be the same size as the gray block because it's twice as big and it's twice as far away. It therefore is the same angular size. Okay.
Right.
So to me, then I was like, well, that should not account for Mount Rainier being shorter than Mount St. Helens. So is there a refraction in the distance pushing this peak down a little bit within our visual field? So I did some searching, and you can see that from this point, there's a large body of water between the two. And so to me, that's possibly what's causing some turbulence in the air, creating a bit of a refraction behind Mount St. Helens, but before Mount Rainier. And so when I do the calculation that way, I come out with 2,966 feet loss versus what we see in the picture of 3,580. So I'm off by about 500 feet. So again, the greater the distance, though, the more the refraction issues, not only just over water, but just air in general. And so if you change the calculator to 0.33, feet per mile squared, you come out with that's the exact number that you should. So it's all just refraction, in my opinion. And then the last part here, so I keep saying last part, but this whole personal dome issue and why we see angular size issues with the sun or why we don't see angular size issues with the sun. I know Walter Bisley, he's not a flat earther by any stretch, right? But he actually put together a decent, and I believe he did the model, right?
I think that's on his website. Yep.
It's actually good. So kudos to him for doing that. But you can kind of see how for some people the North Pole issues and the South Pole issues can be resolved by this personal dome. And I know you've talked about that. It's been talked about on Globebusters and so forth. But to me, what is causing the personal dome, right? And I don't know if upward refraction is truly a normal phenomenon. In other words, temperature increasing or decreasing with height, such that it creates a pretty dramatic effect on what we see. Then that, to me, you can see how I bent these rays of light for a sun, Anyway, I'll put it to you this way. I took basically Soundly's bridge and I reversed it. So what would you see if the bridge was now high up in the sky and moving away from you, but your light rays were getting bent to the observer in an upward manner? Mm-hmm. You would see the bridge essentially bent down to your eye line. And so I kind of tried to represent that here with this blue thing. When this does this, it's going to diminish in angular size to lesser of a degree because it's not moving as far away from you. It's kind of being refracted and brought inward towards the observer. And so that's how I envision this anyway. And so instead of the sun moving away on a straight line, it's possibly moving down on an arc. And that may be why, the angular size doesn't diminish quite as much, is because it's more on an arc and less on a straight line. And that's, I know it does change in angular size, and it does a whole kind of crazy stuff. So I don't want to get into that too much, but I just know that whenever we talk about these issues and we talk about real like floor examples and all these, it's always brought up. Well, what about the sun? Right? It's like the Achilles. It's like they know it's a complex subject, and they know it's like the go-to is like, well, what about the sun? So, well, here's a possible scenario for the sun. And I gave this a big if right here, right? I don't know. It's totally speculation on my part, so people can use it or not use it. I don't know what I think it is a personal dome effect. I don't know what it's caused from. This may be part of the formula. I don't know. So again, this is the overall argument. Things can disappear with distance due to a variety of things. And I saw someone debating the other day, well, first it was perspective, then it was diffraction, then it was refraction, then it was obstructions. Which one is it? And they were getting frustrated, right? Well, to me, the answer is it's all of these things. Right. Or it can be any one of these things, or it can be a combination of these things. And the issue is complicated. And I think all of these things have a very plausible explanation. And I hope I've imparted that to people, that each of these things has a very a simple way of creating this obstruction issue that we see. So again, so what is this? That's my main point of the presentation, right? Is it this, right? The bulge of Earth set across a straight eye line, or is it more something like this, like we see in every hallway or in every example of perspective that we know of? And so again, this is the take home to me. Things get smaller as they move away. Your horizon rises to eye level. You do not continually shift your eye level downward to see a falling horizon, right? All these Earth curve calculators. So, and again, I'll just kind of close it out here. We don't know it all. We may never know it all, and that's okay with me. And to me, our knowledge of what we're supposed to see of this world is guarded in the end. I don't think we're supposed to kind of become immortal mini gods ourselves. Right. I think we're supposed to kind of figure this out by more of faith and not trust in ourselves. And so that's how I go through my life. So I hope I've imparted that a little bit on people too. The biggest thing is for me is if you realize the Earth is flat, then just realize that we are here for a limited time, and you are quite possibly a being of some kind that could live for a very long time beyond this lifetime that we know. And if you believe that to be the case, then you got to make the most of every minute you have, because again, life is short for while we're here.
Choose your actions wisely.
I agree.
All right, and for as far as the super chats, we got a super chat from Ruhif, who said, "I'd love to have a hangout with Travis. Hit me up." We got Tim Drake, who said, "Israel hell." Thank you very much for that. The Mind of God sent one, and Simon Hart. So thank you guys for those super chats. I do appreciate it. That was an excellent presentation tonight. I want to thank Travis so much for joining me and presenting for us. An amazing amount of information that is, I don't know, in my opinion, of the utmost importance to anyone who's even, trivially looking into these topics. And it's not easy because socially you will be ridiculed, you'll be made fun of, and, this has been the defense against flat Earth for as long back as anyone can imagine. By putting it in the mainstream as idiotic, as an ancient desert wandering belief, they've effectively steered any kind of real research, any real testing, any real questioning from ever being even considered. So, showing Israel crashing on their attempt to land on the moon today is just another way to try and show flat Earth research as idiotic. How do these people question the shape of the Earth when Israel crashed on the moon? They need spherical coordinates. They need mathematics. Or the craft would never get there. Would never make it to the moon. So there's basically a concerted effort against looking into this line of research. Everyone's noticed it. It's as obvious as day. The joint efforts of Nat Geo, the History Channel, BBC. I mean, Brian Cox has actually said that to his knowledge, no person has ever thought that the Earth was flat. And people gobble it up. They believe that. So when you see a presentation like this, I really hope that you start to see why they don't want you looking into this. Because there are other explanations. Just like Travis said, there are better explanations. Explanations which take reality into account, take optics into account, and not try to explain the world to you mathematically with no regard to any kind of experiment or testing, and just simply, you better believe it because math is reality. This is the way it is. Simple equations like those involved in relativity, the bending of theoretical space-time, they're all equations built by these men with no way to prove that they have basis in reality. So what Travis did tonight is show how the math involved matches reality. So excellent work by Travis. Travis, any final words for the audience or where they can find and support your work?
No, I just say, check out the videos if you want a little bit more in depth. I think the video number 4 of the series of 6, I go into a lot of stuff I think that wasn't really covered here as far as like refraction and really looking at Red Pill's footage. He caught an amazing day that I don't think anyone has caught to that level before. So I encourage everyone to look at